Assalamualaikum and very good day. So today we are going to learn about 11.2 radioactivity. Radioactive decay is the phenomenon in which an unstable nucleus disintegrates to acquire a more stable nucleus without absorb an external energy. Okay, so radioactive decay is happen spontaneously. There is unplanned, cannot be predicted, independent of physical conditions such as pressure, temperature, and so on. For your information, there are three types of emission evolved during disintegrations. The first one is alpha particle, which is consists of two protons and two neutrons. So it is identical to a helium nucleus and its symbol is 4,2 helium or 4,2 alpha. So it is a positively charged particle and its value is positive 2e with a mass of 4.002603 U. So as you can see, this is the general equation for the alpha decay. Okay, the second emission is beta decay. So beta particles are electrons or positron and sometimes it's called as beta minus or beta plus particle. Okay, beta minus or electron is a negatively charged particle with a negative 1e and its mass equals to the mass of an electron. Okay, the symbol is 0, negative 1e or beta minus. So as you can see, this is the general equation for the beta minus decay. And then for the beta plus or positron, it is a positively charged of positive 1e or antiparticle of electron, but it has the same mass as the electron. So the symbol is 0, 1e or beta plus, and the general equation for the beta plus decay is represented by this equation. Okay, the last one is gamma ray emission. Gamma rays are high energy photons or electromagnetic radiation. So the emission of gamma ray doesn't change the parent nucleus because it has no charge, okay, and has zero mass. So a gamma ray photon is emitted when a nucleus in an excited state makes a transition to a ground state. So the differ between gamma rays and X-rays of the same wavelength only in the manner in which they are produced. Gamma rays are a result of nuclear processes, whereas X-rays originated outside the nucleus. So now we are looking at the comparison of the properties between alpha particle, beta particle, and gamma ray. They are differ in charge, okay, and alpha and beta both can be deflected by the electric and magnetic fields, meanwhile gamma ray cannot. And for the ionization power and penetration power, alpha has the strongest ionization power, meanwhile gamma ray has the most strongest penetration power. Okay, and for the other properties you can see on your own. Okay, next is decay law. The law of radioactive decay states that for a radioactive source, the decay rate dN per dt is directly proportional to the number of radioactive nuclei, which is N, remaining in the source. So we can use the equation of dN per dt equals to the negative lambda n. So please take note that the negative sign means that the number of remaining nuclei decreases with time. So we also can use the another equation which is n equals to the n naught exponent negative lambda t, where n naught is the initial number of nuclei, lambda is the decay constant, and t is the time taken, okay, during the process. Okay, lambda or decay constant is defined as the probability that a nucleus will decay in 1 second. The unit is per second, and the half-life is defined as the time taken for a sample to become half of the initial number of nuclei. So the equation of the half-life is ln 2 over lambda, or 0.693 over lambda. So as you can see, the value of the half-life or the unit is depends on the decay constant. Okay, next is activity of radioactive sample, where it's defined as the decay rate of a radioactive sample. So the equation is A equals to the dn per dt, or equals to the lambda n, and there is another equation which is A equals to the A naught exponent negative lambda t, where A is the activity of the nucleus at time t, and A naught is the original or initial activity. So please take note about the sign convention in the table. 1 becquerel and for 1 curie equals to the how many decays per second, and please don't forget that the unit for the activity is the decays per second, curie or becquerel. Okay, now let's do this exercise 11.2, which is question number 2. A drug prepared for a patient is staggered with TC99, which has a half-life of 0.5 hours. So what is the decay constant of this isotope? Okay, so from the half-life, which is T half, equals to the ln 2 over lambda. So the decay constant is lambda equals to the ln 2 over T half. So the half-life is already given in the question. So we just substitute the values and we will get the answer as just like that, 0.115 per hour. Okay. For B, how many TC99 nuclei are required to give an activity of 1.5 microcurie? So from the equation of activity, which is A equals to the lambda n, okay, and you need to know, you need to understand that for 1 curie, it is equals to the 3.7 10 to the power of 10 decays per second. So we have to substitute the value of the activity in unit microcurie into decays per second, and so does the decay constant. So we have to convert it 0.115 per hour into per second by dividing it with 3600 second, and then we will get the number of nuclei, which is 1.74 10 to the power of 9 nuclei. And for the last question, okay, determine the drug's activity after 2.05 hour. Okay, so from equation of A equals to the A naught exponent negative lambda t, we just substitute the value of the initial activity that we got from B, and then lambda t, okay, lambda in unit per hour and t in unit hour. Okay, so we will get the answer as 1.18 microcurie.